Good morning, everyone. So I'm happy to present you a course about quantum trajectories. So my goal is just to introduce the concept of quantum trajectories and then talk about some results about quantum trajectories. So we'll talk about limit theorems and also the spectral gap of the Markov pattern we will see later. So today, the goal is just to introduce the concept, the model, how to modelize mathematically the quantum trajectories. And then in the rest of the week, we'll introduce the objects we used to study this Markov chains called quantum trajectories. So first, I would say I'm not a physicist, so I will just give a quick modelization of the problem, and then we study it mathematically. So what is the problem? So our goal is to measure the state of a quantum system. And if we measure it directly, then we'll fix the state of the system and we won't be able to continue to see the evolution of the state. So what we will do is what we call an indirect measurement. So we'll take some probes. I will call it P1, P2, P3, etc. And we will perform a measurement on the probe. And because there is an interaction between this probe and the quantum system, with the intrication, we will be able to measure the evolution of the state of the quantum system. So if, for example, my initial state is for 0, so we will explain what it is later, then with this measurement, I will be able, by some way, to deduce the next state of my system. And then, after this measurement, I will choose another probe, P2, and after I will get some O2, etc. And with an infinite number of probes, I will be able to measure, I will be able to get the evolution of my quantum system. So what is the main idea of this quantum trajectories? And for example, Serge Haroche got a Nobel Prize based on this kind of indirect measurement. So now my goal is to explain it mathematically. So how can I model my quantum system and the state of my system? So for us, all the quantum system will be described by Hilbert space. And we will take it complex. And in the rest of the course, we will take it finite dimensional. About how I describe my quantum system. Then I want to know how to describe the state of my system. So in which state? And so to describe the state of the quantum system, we'll use what we call density matrices. So states of the systems. are described by density matrices. And both these matrices are the space of matrices which are auto-adjoint, positive, and of trace 1. And so among these density matrices, there are a subset which we call the pure states. So pure states. So there are rank 1 projector in actually, if I give like, for example, I say this this space is called, for example, pure, for example. Actually, the convex hull of the pure states are these. So convex hull of pure, dipolar D, and as external point of my density matrices are the pure states. So they are really special states in my space of density matrices. Okay? And for later, let's just give some interesting property of these pure states. So every pure state can be written or to some projection onto some vector x. And if I have this, I can give the representative of x in the complex projective space. So, for example, x hat is a representative of x in the complex projective space. So there is a bijection between the set of pure states and the projective space. And the complex projective space.
Right? So
Yes.
Yes. This is D minus one dimensional complex sphere, right?
Yes. Actually, you don't care about what's about the norm of the vector,
Okay.
just the direction. Okay. So now, let's talk about how evolves the state of a system. And for this, I will introduce the quantum channel. But before to introduce the quantum channels, I have to give some definition about linear maps. So I have three definitions to give. So let's see a linear map from the complex matrix of size D. So I will define what is a trace-positive map and a positive map. So we say that phi is trace preserving if for every phi in rho, namely, we have traces of 3 or 4 equal trace of 4. So it's quite natural to create a trace by on Mars. Then we want to define what is the positivity. So here we say that phi is positive if for every rho positive, we have the trace, no, sorry, have phi of rho positive. So here we have the positivity, and there is something also stronger than positivity, which is what we call the complete positivity. And so we say that phi is completely positive if for every integer L now we have that the map identity of the matrices of size L tensor product with phi is positive. So we are seeing it like in here is the product tensor product of my two maps. So we can see it as a linear map, and we have the definition of the positivity here. So here we want this to be positive for every L. And so now we can ask ourselves, okay, why did I present you that? Is actually the evolution of the states of my quantum system is linked to what we call a quantum channel, which describes the evolution of my state. And what I say just now is that the quantum channel are exactly the trace preserving completely positive maps of N. So, definition. Quantum channels are completely positive and trace preserving maps. And we will call this later this CPT. Okay. So now we know how to give the evolution of my state. However, like this definition is a bit, I don't know. If you look at it, it's hard to give a good expression. For example, if I ask yourself how to create a trace preserving map and a completely positive maps, at first thought we don't have a good idea to how to construct it. However, there is a good decomposition of such maps, which I give now. So it is a theorem. So P is CPTP if and only if there exists K I decay like this in MB such that P of O is equal to the sum to I decay of VX O I, and we have this and we have the equality, and actually this equality is what we call stochasticity relation. And this operator, so this matrix VI, is what we call the cross operator. So the matrices VI are called cross operator. And so now we change our problem to how to give a complete positive trajectory map as only finding some VI, verifying some equation, and now we know that every CPTP map is written like this. So now, if I want to study the evolution of my quantum system, it just depends on this matrices VI. So now I will just look at this VI and where they live, and to study my quantum trajectories, I will just have to look at them. Okay. So now, after presenting all this notation, we can go back to how, in reality, everything works. So let's go back to quantum trajectories. So now I will take back some VI. So we will take them. Let VI one plane cross operator. So in the single quantum channel. And okay. Now my goal is to present you how this the state of my system will. So I go back to my drawing. So let's take my quantum channel here, my quantum system, and all the poles. So actually, At first, I was talking about the measurement, but what do I measure when I measure? So here, the set of my possible outcome of my measurement will be given by my I from 1 to k. So I can give an alphabet here, which means the possible outcomes of the measurement. Okay. So here I perform my measurement, and I can measure 1, 2, 3, 4, 5, okay, until k. And my question is, okay, but what is the probability to measure some, for example, what is the probability to measure 3 or 1 or 2? So here, actually, the quantum mechanics theory says that there is some probability given by my operators, my cross operators vi here, and also the state of my system at the time n. So for example, let's assume that the initial state of the system is some rho 0. So actually, the probability of measuring I will be equal as a trace of VI or VI star. No. And so you'll see that it depends actually on the state of my system. So if I had like another initial state, for example, I don't know, rho 0 till, it will change my probability measure. And so a good question you can have is, okay, but is it a probability measure? Because if I sum everything until 1 to k, does it give what? So it is a good question. So indeed, it is a probability measure. If you take the sum, so from 1 over k to p of measure A, you get the sum 1 over k of the trace of bi rho bi star. And then, because the trace is linear, you actually get the trace of P for rho zeros. And because the quantum channel is trace preserving, you get the trace of rho zero, and then you are equal to that. So you have indeed a probability measure. Okay. So now we have some probability measure to measure some outcomes. But the real question is, okay, it's just my results. It's not how my state evolves. So there is a difference between the outcomes of my measurement and how my state will be updated. So how does my state evolve? So the evolution of the state. So if I measure I, if we measure I, the new state of my system will be ρ1 given by vi ρ0 vi star divided by the trace. And we remark here that indeed this new state is still a density matrices. So, and actually it's something I didn't mention before, but when you look at a control channel here, it sends the space of density matrices to the density matrices. So the density matrices space is invariant by phi. And so here we have a new state. So now you are step 1. But we want to know, okay, what happens if I perform a second measurement? So now my new state is ρ1. So I have to do everything I did here, but by changing my ρ0 here by some ρ1. So everything is the same. The only thing I change is my probability measure. So my probability measure change at every step to the probability measure to measure my outcomes change at every steps. So, for example, I will just do a quick Markov chain drawing. So we'll assume that there are only 2 matrices. Example, matrices V1 and V2. So let's start with ρ0 with some probability trace of V2 ρ star. Yeah, so probability trace V1 rho V1 star. We get some, let's say, 1, 1, and 1, 2. And for example, if I manage to measure 1, this one is selected. And then same, here we have some new probability, but that will depend on my new state here. So here it will be traced on V1, 0, 1, V1 star. Trace on V2, 1 star. And we can get either this new state or either this new state. And so we can go on, and we want to know, okay, if I did n measurements, can I have some probability? Can I give a probability measure to measure? For example, if I did n measurement, I get I1, I2, I3, I4 until IN, and I say, okay, speed of measuring a sequence of outcome. Okay, so my goal is to give you this measurement. And so for this, let's say what happens. So here, that means that my new my new state is if P of measure I1 IN, knowing that I measure some I1 until in minus 1. So here we are in state, I call it rho n minus 1. And so here is just the trace of the in rho n minus 1, in minus, oh, this in is and the update of my state is the following. If I'm at the state rho n minus 1, assume that we are at the state rho minus 1 at time n minus 1, then 1 is equal to vi for n minus star pi star under the trace with probability minus vi 1 minus 1 vi star. And then actually, if you look at it, then we have like, okay, every time multiply the matrix. So actually, if you go on and go on and go on and go back to what happened for the row, actually, we have some product of matrices at the left, product of matrices at the right, and actually, if I define Wn, which is equal to Vin until Vi1, the new state, rho n, is equal to Wn, rho 0, Wn star, divided by the trace of the same thing, and with probability trace of my outcome. What we have here is that the probability of measuring I1 until In is equal to this thing. So we have put it Wn, so there is a small mistake of notations, but here just going from I1 to In, it's just my product of my outcomes. So as I have written here. And so now we have these things, okay? So now we are able to give probability of measuring some outcomes and how does my state evolve based on the outcomes. Okay. So now I just want to talk about a specific case. So, oh wait, I said, sorry, almost to say the real thing is that this sequence ON is what we call the Markov, the constant trajectories. Okay. Now I want to go back to a specific case, which is a case of when we start the pure state. So here we did everything with an identity matrix, but we want to know, okay, if I start with a pure state, can I say more about the quantum trajectories?
I have a question.
Yes.
So the stochastic process is like given a matrix rho 0,
Yes.
and you multiply by VI and the VI transpose, and
Yes.
you normalize.
Yes.
This gives you the next step, right?
Yes.
And with the probability given by the phase. And I understand this right now, but what do you mean by measure IN to I1 to IN? So does it measure the mathematical measure, or?
No, it's just like when here the measure is when you look at the probe, you do some measurements. It's like you imagine you have all your probes and you perform a measurement of it. So here, the first one will give you I1, second one will give you I2, third one, etc., will give you I3 until the last one, which are every possible outcome. So my outcomes, since here I took a finite number of cross operator, I have k possible outcomes.
Oh.
So it selects a matrix. So actually, if you start, for example, for rho 0, then the outcomes will select the n matrices. So for example, if I have two matrices, maybe let's do an example. Let's say n is equal to 4. Okay.
Okay.
So I can have different outcomes, and yes, and have two matrices. Everything which will be. So for example, I have 1, 1, 1, 2, or I can have 1, 2, 1, 2. Okay. So here, for this sequence, it will be a delay. So we have V2, V1, 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 because we go by the left. So here is the last one I measured. Then I will have my rho 0 here. And then I will have everything star, so the same matrix. And this will be divided by the trace. This will give me my new state if I measure 1, 1, 1, 2. However, I could have measure 1, 2, 1, 2. Okay. So if I measure 1, 2, 1, 2, then you have V2, V1, V2, V1. The same. Divided by the trace. But actually here, since I have n equal to 4 and 2, I have 2 as a power 4 different possible outcomes because I measure n among k possible outcomes. So here, actually, for every n, the possible of different outcomes is equal to k as a power n.
Okay. So like this measure I1 to IN actually records the index in the WN. Right?
Yes, yes.
Okay.
Yes. It's true. It's like, okay, it's more priority. I will talk about this a bit later. To say, okay, here it's more like the extension of Kolmogorov of my.
Okay, very clear. Thank you.
I also have a question.
Yes.
So to write that way, the probability of I1, IN is equal to probability of IN knowing the first n minus 1 outcomes, and then to write the probability, you implicitly assume that the measurements are completely independent, right?
No.
In a sense that each time you just
yes,
start something which is independent from.
Yes.
Yeah. Okay.
I just want to recall that, okay, now I perform some measurement, I have a new state, which is no one. And now I perform a new one, which will depend on my one.
Okay. Yeah. But is there any sense to consider some dependence of the previous states or not? Not at all. I mean, if from physical point of view, I mean, here you said that it depends exactly on the last state, and I forget what happened before.
Yes.
So is there any physical sense to consider measurements which depends not only on the last state, but somehow there is a trace of what happened before, or it does not make any sense physically?
I don't have an answer. So.
Okay, thank you.
Yes, maybe. Okay. So now I want to present you what happens when we take some pure states. So I will just remind you what are pure states. So we will consider O0. It will be a projection onto some X naught. And actually, we have some relation. So I will just say that X naught is the representative in the complex projective space. By not. Okay. And then we have the following relation, which will be useful. So here we are looking at these traits. So actually, if you are looking at these traits, but for projections towards some X, you are actually equal. So for at this norm at the square. Okay. And then if you look at VI, the projection VI star divided by trace, it will be equal. So as an operator, as a projection towards VI X naught. So here I will just like there is some abuse of notation, so I say okay, the representative could be the vector and vice versa. And here I will just define what it is here. So here VI not X0 is the representative of the normalized vector VI X0. So actually, now, when you do an evolution of your quantum trajectories, you actually stay in the pure state. And moreover, you say that what evolves is the vector towards the project. So actually, you have this have an induced Markov chain. The Markov chain rho n induce a Markov chain on the complex projective space. We call it Xn, such that Xn will be equal to Vi point n-1, Xn minus 1, sorry, with probability Vi Xn minus 1 square. And here, X0 is consider norm one. We consider norm one vector for x naught, because you can take any one actually, since we just care about the direction. But when you are doing your computation, you start with a norm one vector. Okay, and that's why here also my new xn will be also of norm one. And when you have this, like you play a game between the space CD and the complex projective space, but you always take here some xn of norm one when you're looking at it. For example, here, your the norm of your vector here. Okay.
You need hat in that formula in the box, right?
Here.
Yeah, because you divide by the norm.
So you don't need it. It's just like more an abuse of notation. You don't need hat here.
No, on the right hand side. I mean, you write hat
here.
Yeah, you write hat to.
Yes. Like it's my. You can do it without the hat. But it's just.
No, because what I'm saying that hat is already a member of the projective space, right?
Yes.
X0 hat, and then you divide by norm.
Yes. But you don't need the divided by norm, because you let me just like, actually, if you look at what will be your x1 as your norm of norm one, your x1 will be the x naught divided by its norm. Okay. And your, so here will be your x1 actually. The complete expression, just not vi x naught. Because if you look just at vi x naught, it could be not of norm one, so you divide it by its norm to get something of norm one, and then it will give you your x1.
Okay. So, do I understand correctly to say that you start from a pure state, then you always remain pure?
You always remain pure.
Okay.
Because you have this relation. So here, with this, you stay like this. And actually, you preserve the pure state with your evolution of your trajectory.
Okay. And if by chance this vi x naught is equal to 0, then
so if vi, it's a good question. So for example, if vi x naught is equal to 0, there is not an issue, because that means you won't measure vi, because your measurement is with probability vi x naught.
Okay.
So you won't measure. So when it makes sense, it's because it's not 0. But yes, it's a good question. Okay. Okay. So now I just want to show you also the relation between this and how does it evolve based on the first state, and also this product of magnitude, so like we have seen later, just previously. So at the state n, as before, we have the xn will be equal to some wn x naught and so here wn is the random variable. So I will explain more later, but this represents outcome of the measurement. So, of course, it's not the measurement. It's not the measurement which are described here, but we saw just before that the measurement gives you this random product of matrices. And actually, I will define more later properly this random variable, but like you have your random measurements, which give you your matrices. And actually, we will be able to create some random variable for every step. And we have some WN. So we do it like this. So we can just say that omega is a space of MD. And at the power n, you can have VI the omega equal to VI for omega one, etc., which is in omega, shows the random variable. Until the matrix chosen. N is my folder on the n first on the variable VI. And as we've seen previously, all my VI have different laws based on the previous state. The law of my VI depend of the state of my xi minus 1. Okay? So now, before to jump into the results, I want to spend some time about the assumption we can do on the matrices. Because for instance, I just talk about everything here, but my VI just live in MD, but they could live anywhere. So, and since there's a crucial, actually everything depends on these matrices. So, of course, everything we can get about these matrices depends on where I live. So, the first assumption I want to talk with you is an assumption called contractility assumption. But in the context of for people who are looking at random walls on the matrix group, so in the field of algebra, people are also calling this proximality. And in the context of constant trajectories, we'll see that it's linked with the purification assumption, which is more in the context of today's course. But here I want to introduce as a contractility assumption because it's more easy to talk about this assumption because the purification assumption is a bit more complicated to look at it. But just keep in mind that we have three different views of this assumption. We are not completely equivalent, but in our case, they are. That's why I can choose any this, but like the three assumptions are not equivalent in absolute sense. So what is this assumption of contractivity? So we will take some T, a subset of my set of matrices, and we will say, and here we will construct some object. So no, let's not call it T with a place A. We say like T0 is just identity. So we can start with identity. And then for n strictly greater than 1, we say that Tn, so it is the possible finite product of size n of my matrices living in A. So it's like here, all the possible product with n matrix in A. And what will I construct is T, which is just the union of all my Tn and T0. So that means this set actually contains all the possible products, all the finite products of my element in A plus identity. And so the contractive assumption says the following thing. So A verify the contractivity assumption. So if there exists a sequence, we call it WK in T, so that WK divided by its norm converge to some W infinity, a matrix of rank 1. So here, let's take some example to know how to verify such a property. Like you say, like if you look at it, it's hard to. If I give you any A subset of matrices, knowing it's contractive or not is very hard. We have a good way to know how to look at it. That's why, well, I spoil maybe the future, but we see that every result we have is based on this assumption. But we would like later to remove this kind of assumption because when you look at it, it's hard to verify. So
this double infinity is not necessarily orthogonal projection, right? Just have one matrix.
Just a matrix of rank 1. Yes. And you only want one. So let's take some example to know when it can happen. So for example, if A contains one rank 1 collector, it is okay. One rank 1 matrix, it is okay. So if A contains one rank 1 matrix, so we can call it, I don't know, A. No, that's it. Then you can just choose the constant sequence equal to U divided by U, and it works. So if your set contains a rank 1 matrix, it is completely okay. You just have to take your constant sequence, and it is okay. We take a second example, which is more a counter example, which is the following. Imagine that A is a subset of the unitary group. So that means that if you look at of your final product, it stays in the unitary group. And then when you take the limit, you stay in the unitary group. So that means it is impossible to get a matrix of rank 1. So you cannot verify the assumption. The UN of C is a compact group. Okay. So here we have two easy example to verify, to not verify. But as I said previously, in general, it's very hard to verify this kind of assumption. Okay. So now, with its assumption, my goal is to link this with quantum trajectories, and especially with what we call purification. So, link with purification. So, let's define what is what we call the purification of a quantum trajectory. So we say that the quantum trajectory purifies when asymptotically it approaches more surely the set of pure state. What does it mean? That means that here I have my base density matrices. Also, it's a bad drawing, but let's say that my two sets are here, and I let my quantum trajectory evolve, and almost surely my quantum trajectories will fall in this set of pure state. And as I said later, when you are in your pure state, when you continue to evolve your quantum trajectory, you stay in the pure state. So what does it mean? That means that if I know that my quantum trajectory is purified, that means I just need to study it on the pure states, because everything which happens before is not useful, because I know that asymptotically I will be pure. So now the question is, okay, how can I purify, and do I have some way to prove that my quantum trajectory is purified? Hence is the theorem of Kummerer and Masson. Sorry. And what they said is the following. So here I call it contractivity. So under the contractivity assumption, so the quantum trajectories this quantum trajectory is verified. And so it's very good for us, because now, starting from there, we will always assume the contractivity assumption. And that's why we will only study the quantum trajectories on the pure state. Starting from now, we'll assume the contractivity.
I think it's not independent of a set A. So I guess your A is the
Yes. Sorry. Yeah. My A is equal to here and my set here one. Sorry. So here also, everything I'm doing is on a finite number of matrices, which is just for the sake of simplicity, but it could be generalized for a measure one day. But I will do everything with finite number of matrices. So it's not an issue if it's not finite here. Okay? So now, let's talk about this first assumption. Let's introduce the second assumption that I will call irreducibility. Okay, so again, let a subset of NB. And so we say the set A verifies the irreducibility assumption. So if there does not exist a subset space E, included in C D, such that so E must be different of the whole CD, and such that KE is equal to A. So that means there are no other, the only invariant subspace by A or CD and 0. So that's what we call the additivity assumption. And there is a stronger assumption than this. So I will also define it. But what we call the strong additivity assumption. And here, so what is a strong additivity assumption? Is that there does not exist so we'll call M in M and E1 EM the space of CD such that E of my E of sorry is invariant by A. So here it's way stronger than what we had here, because if we had, for instance, only the additivity assumption, you could have like so let's erase here. So you could imagine the following situation where you have your E, so we take only 3. So if you verify the additivity assumption, that means that you can go back to your subspace. But you could have like you apply I, you go to E2, you apply I, you go to E3, you apply you go to E1, and you could have like this kind of rotation. And this M is what we would call the period of, well, we call the period for some reason, but I will maybe explain it later in the course. And so this can't happen if you verify the strongest assumption, because here if you take it, that means that you stay in the union of E1, E3. So this assumption is very crucial in the context of quantum trajectories. And actually, every result on this, you cannot remove this assumption, and there are some counterexample if we remove this with this assumption. However, the results I will introduce you a bit later could maybe generalized without the contractivity assumption, but we'll talk about it later. So let's take an example of a quantum trajectories that verify these two assumptions to give a proper example. So I will propose you the following one. It's what we call the bit switch. And so, we take some P in 0, 1/2, and we take two matrices. I will take MK, which will be, sorry, MK of 1. We'll take MQ, which is square root of P square root of Q. And then we take MS, which is square root of 0, 0. And here we pass square root of Q square root of Q. So we want to prove that this is indeed represent a quantum trajectories. To remember that to prove this, we would like that MK star MK plus MS star MS would be equal to identity. So here I take it. So here it will be P and Q plus. So here I will also have a Q and P. And then since Q plus P is equal to 1, we'll have 1, 1, and we have identity. Okay. So now we want to prove that it verifies the reducibility assumption. Reducibility. So to prove the reducibility, that means that we don't want that it keeps invariant some one-dimensional subspace, because here we are in dimension 2, so we have only 0, 1, and 2, so just one. And so we know that it keeps an invariant subspace if we have at least one common eigenvalue. So here we can just look at the eigenvalue of one matrix. So for example, we take MK, and if these two eigenvalues are not eigenvalue of MS, that means that they won't have a common invariant subspace. And so here, the eigenvalues.
Eigenvector, right?
Eigenvectors, sorry. Eigenvectors of MK are 0, 1, and 1, 0. They are not eigenvectors of MS. That form. Verify the reducibility assumption. You can see like that, okay, this assumption is also a bit hard to verify also if I have a lot of matrices. However, it's way more easier than the contractility assumption. Like here's the intuition behind this assumptions are way more natural than the contractility, even if the contractility assumption and the purification assumption, which are quite similar, are also based on physical observations. So it has some physical intuition for the assumption. Okay. So now,
what about strong irreducibility? Does it work here, or strong irreducibility? Strong. Is it also true, or?
Okay. Good question.
Okay, it doesn't matter. We'll discuss it later.
But yes, I will maybe look at it. Okay. So now, my goal is to introduce you properly all the known results for quantum trajectories. and to give a plan of what I aim to do this week. For this, we will introduce more the concept. So left omega will be our and will be this just on that sequence of matrices. So we denote by VI random variable that omega is equal to VI and of flow and VI xn squared and Wn is equal to the product of my random variables. Okay. So now, if nu is a probability measure on the projective space that I endow with some attribute of Borelian speed. So we will define some measure, which I'll call it P nu, on the space nu of cross ON will be the integral of S theorem of my sum over K. So here we have Wn, so my product of matrices, as I said before, and against some x, some x.
And then xn minus 1 or xn the probability? VI is omega, read.
Sorry. It's VR. Sorry. And it's
okay.
Sorry. I mix up all the notation. Okay. My goal is to study the Markov chain. Itself. To study the Markov chain Excel, I want to know what is the Markov operator of my Markov chain. So, Markov operator is f of x of f of some vi, okay, vi x. Well, and so here we just define all the elements. So f is a continuous function of PD. So we say that we look that here we have some elements of the projective space, and it will be some. We can take also our.
Yeah, can you go back to the previous form because
Yes.
I'm not sure I understand. So what is this S and O N?
Oh yes, sorry. Maybe I will take it more higher. So here, let me make this. So let's new quality measure on here we just say new, which is just E of K of lambda V. I can just look at this and here. Yep, just looking at this. Okay. And so here I will take some point measure P nu on omega cross PCD. So I take some ON here. Yes, maybe a sense that S cross CD cross omega. So I take some S here, cross some ON here, and I will have at P nu of S for n. So if I'm taking some subset of my projective space, I will integrate over my measure mu. And also I will look at some ON, which is a subset of I'm just looking at my n first measurement. I'm at n step. So I just have some Wn here.
I'm just looking at formally what is written there. So you integrate over measure, which is measure on that projective space, right?
Yes. Yes.
So this is over the integral over S, right? S is a subset of P, C,
yes.
Right? And then you have a product for N. So what is the measure you integrate with respect to which you integrate? Okay. So you integrate with respect to mu, and then you write it as a sum.
Yes, it took it as sum, yes.
Okay, then the indices are not correct. Then
yes.
WI, and then should be right? Or?
Yes. I missed something at.
No, inside the formula, you have a normal WI omega or WN omega.
No, it's here is WN.
Okay, then where is I? Because you take the sum with respect to I.
Yes.
Sum.
Yes. Sorry. Here it's more like this plus. It will be easier like this. Like you took some measure mu on the and you have suffix. So it's
okay.
So it's just like I mixed up because usually I take it with a measure mu. And here, since I had the sum, I mixed up, sorry. Okay, so let's go back. So here I have f, which is a continuous function. My x lives in the correct space. And here, my x without the hat will be a unique vector. Like you can take any representative of x, but here you will take it such that x is equal to 1. And so here, that means that my operator pi acts on the space of continuous function. And so when we study some Markov chains, actually, so tomorrow I think I will just go back to how to get some limit theorems on Markov chains and the classical technicals to show the difference between this operator pi. But we would like to know how the spectral properties of my operator pi. So for instance, one natural question is, does it have an invariant measure? And if it has an invariant measure, does it have a spectral gap? And after, can we derive some limit theorems based on this property on the operator pi? So now I will state all the results on this operator pi, and therefore the results on the Markov chain Xn, which is our conjunct. Okay. So first we have this theorem. In the 2017, Martin France, Yann Paul France, and Clément Pellegrini. We state the following thing. So under the contractivity assumption, so we call it cont now, and the additivity assumption, so the operator pi has a unique invariant measure. And moreover, we have convergence toward this measure. So, moreover, for every new probability measure on the complex space, we have a new pi at the power n converge in some sense towards the invariant measure. So here it's inverse Stein next. But I will explain this when I will go back to it. So here we just have like, okay, I look at my power of my n, and then this probability measure converge in some metric towards my invariant measure. So here it was the first step towards first step to study the quantum trajectories, and then here we had the invariant measure. So what we want after is, okay, can we get more about its invariant measure? Can we get some spectral gap and etc. etc. But first, with the help of Gianluca Satras, Benoit and Clément Pellegrini, with some martingale approach, managed to prove some limit theorems for the quantum trajectories. So here I will just define an object. So I will show a limit theorem for some object, but they got more. I will just focus on one specific limit theorems. So here we take some G in the space of C alpha. So here I will just define what is C alpha. So it's just the space of alpha algebra continuous function. We undo the complex projective space with a metric. And so if I take such a function, I will define what we call the empirical sum. So we will say that for n, SNG is equal to the sum for k of L to n of G of my sum. So that means I'm summing G applied to the step of my quantum trajectories. Okay. And so now can ask ourselves, can I say something about this empirical sum? So the answer is yes. So if you want to clear the goal by against Benoit, Gianluca Satras, and Clément Pellegrini. And what we prove is, like, I will just state some limit theorem, but first we prove a law large numbers. So one over n of my empirical sum converge indeed towards my the expectation of G by the expectation of G in here we have the invariant measure which appears in the previous results of Tristan Benoit, Martin Fass, and Clément Pellegrini. So we have this, and then we have also a central limit theorem. So if I want to look at the central limit theorem, so for every probability measure mu implicitly, I can look at G minus the expectation with respect to mu of G, and this converge in law towards some Gaussian of parameters, some sigma square, with sigma square is given by some relation, but it's not important for some. Okay, so in addition of this, they also got some moderation principle, also some law of the iterated logarithm, and also some other limit theorems. And to get these theorems, they used, as I said before, the martingale approach, and they managed to, by using this martingale approach, to get all the theorems. Okay. However, with this approach, you cannot obtain all the limit theorems, especially here we have only the central limit theorems, but there is something called variance and bounds when we are looking at central limit theorems. So we will go on it the following days on it. But to get it, it's not possible with the martingale approach. So here, that's why with my advisor, I study the spectral properties of my operator pi and use more a spectral approach to get other limit theorems. So before we say this theorem, I just want to explain what is a spectral gap. So I will do it only for a matrix. So but it can be generalized for the operator. So let P the matrix of size T. We say from the spectral gap there is the gap between the two largest modulus of the eigenvalue vector. If I do a representation, that means the following. Here, I will have my largest modulus of my matrix here. And if I take another one, my second one could be here. And then, so it's like the side term here. That means that among these parts, there are no eigenvalues here. And the spectral gap is very useful to derive some limit theorems. So here I did it for a matrix. However, here my operator pi is not acting on a finite dimensional space. It's acting in the space of continuous function. So of course it's an infinite dimensional space. So here it will be, of course, harder to prove that pi admits a spectral gap. However, it will be linked to what we call quasi-compactness, and that's why my goal is also to introduce you to this world of quasi-compactness and to show you how to prove that this operator has a spectral gap. Okay. So let's just state the theorem. So it is theorem of 2025, so very recent. The operator phi acting, so it is important on the space of alpha under the function. And the spectral. Okay. So now that I explained everything here, let me just explain what is my goal of the problem. So, what I want to do is some reminders of the theory of Markov chains. Why do I want to do this? Is because I want to be sure that everyone knows how to study these Markov chains and to show the difference between the quantum trajectories Markov chain and the usual techniques we use in Markov chain, because this Markov chain is really not a Markov chain we can classically study, because, for example, so it doesn't verify the fear additivity assumption, which is very important when you're studying Markov chains. And so my goal is really to go back to this and show how show the difference between the two models. I also would like to show how to get limit theorems by perturbing the transition matrix of the Markov chain. And why do I want to do this? Is because I want to show you that, okay, everything we do in finite dimension could be adapted to infinite dimension under some assumptions. So here, by doing this, I will arrive at my second goal of this course, is an introduction to quasi-compactness. So what does it mean? So I will just give the definition here of the quality compactness to show you the analogy with finite dimensional. So next time, that's Q. It's quality compact on a Banner space B if there exists two subspace of B, F and G, such that so we want so first we want that B is equal to F plus G. And secondly, we want that Q, we want that F is finite dimensional. And then we want looking at the spectral radius of Q, rho of Q is equal of rho of Q of F and rho of Q restricted to G is strictly smaller than rho of Q. That means that if we're looking at this decomposition, like we have the decomposition of my Q, which is the decomposition Q on F and Q on G.
But you don't assume that they are invariant, right? You just project from left and right, or
yes, but actually we will they will be invariant.
They are invariant, or not necessarily. They are necessarily invariant in your definition, or
yes.
Okay.
And actually, yes, we because we have this decomposition, and so we have also the invariant of. So that means that our Q will be equal to some Q on F plus Q on G. And since we have this equality, that means that when I will look at the power of n, so the ID will be that Q at the power n will be equivalent at just the projection onto F. And that means that since F is finite dimensional, everything I'm doing for a finite dimensional setup for Markov chains will be adapted to my operator. So my goal really is to introduce you to this theory of operators, showing how to obtain such a decomposition, because for the moment, we don't have an idea to show such a good decomposition. And then to show how to derive limit theorems based on this decomposition. So this is my goal for this introduction to quasi-compactness, and it will certainly be a bit longer. I will give you a lot of different examples to familiarize with such a concept. And finally, the last part will be application to the problem of electrons. And here we will use everything we learn about the technique of Markov chains and the technique of quasi-compactness to show all the results I presented just before. And in the last part, if we have time, the further directions. So here in all the results, I assume the contractility and the reducibility assumption. So we can ask ourselves, okay, can we remove some irreducibility? If yes, which one we can remove, which one is not, which one is very important? Do we have some counterexamples for when we remove some of these assumptions? And I hope I have time to do everything here. And I think we are close for today. Like, I think it's better to start completely this thing tomorrow, if possible.
Yeah.